In this lecture, we will see more about this microwave remote sensing. In my previous lecture, I already covered little bit of introduction as well as what advantages and disadvantages we have when we are using microwave remote sensing. So, let us understand more about this microwave remote sensing. So, let us start with what are the different types of radar system we have till date. So, this is the first type where we have pulsed radar. So, in pulsed radar, distance between transmitter and object can be measured, and the speed can also be measured by constantly tracking the object, that is change in range from pulse to pulse. So, when you are having track of your transmitter location and the object location, so this is possible, you can track the speed of the object. So, if you have a pulse radar installed somewhere and you are looking at maybe a moving car, you can easily track them, but here we have another type of radar which is actually more suitable for that application. So, in continuous wave radar, we have Doppler radar and frequency modulated continuous wave radar. So, in this case, it is more suitable for your measurement of speed of any vehicle, and nowadays people are using it. So, police have already installed this in traffic signals and they are monitoring the speed of the car. So, these continuous wave radar, they are actually used for aircraft altimeter, but these are not suitable for long distance range measurement. So, in this case, we have two different types of radar system. First one is pulse radar, another one is continuous wave radar. In pulse radar, distance between transmitter and object can be measured and speed can be monitored, that is because of the change in range from pulse to pulse. Whereas in continuous wave radar, you have two different types of system. First one is Doppler radar, second one is frequency modulated continuous wave radar, and continuous wave radars are very popular nowadays and people are using it for day to day life purposes, right. Now, here let us understand what are the different types of component we have in microwave remote sensing. So, the main component of radar system are transmitter, receiver, antenna, electronics which records the received energy, right. So, here in this figure you can see this is in case of active radar system, where the system itself has a capability to illuminate this particular surface, and the surface will react and then it will give you the back scattering value, right. So, the scattered value will go back to satellite or your sensor, which is located either in the space or maybe in airborne, right, and that will be captured by this particular sensor. So, here you can see this particular system has illuminated this area from this particular position, but whereas in this one here it has moved and it has captured the back scattering values. Now, let us understand here the satellite which is illuminating this particular area will release the pulses, right, and the moment the first object which interacts with this echoes, right, that will get back scattered and this will give you back scattering values, right. So, the back scattered value will again go back to your satellite or sensor, and then that will be recorded, and subsequently the recorded data will be transmitted to your ground station, and the ground station will receive that energy and in form of image, and that will be distributed and analyzed. So, this is how we are doing in case of microwave remote sensing, right. Now let us understand this backscattering. What is this backscattering? How it is different from reflectance or emission? Here already you know this particular flight has active radar and it is illuminating this particular surface, and the surface will either absorb this energy, transmit this energy, or reflect this energy, or scatter this energy. So here, since we are talking the microwave remote sensing data, so here microwave energy, they are the longer wavelength and they will get back scattered, right. So the back scattered value will be received by this object which are scattering this or which is involved in this scattering phenomena is known as back scatterer, right. And the energy which has been received by your active microwave sensor, that is actually that energy is known as back scattering, right. Let us understand what exactly is happening here. The transmitter generates successive pulses of microwave A. So the microwave energy, right. So the successive pulses. So the pulses will be sent in a FOV and that will reach to our surface, and the moment the object interact with your pulses, they will start back scattering, right. And the same time it will go back, right, like this, and it will be recorded by your sensor. So in between, the radar beam illuminates the surface at a right angle to the motion of the platform. So this is the movement direction in this case, right. I cannot draw the third direction, so this is actually for the visualization. The antenna receives a portion of the transmitted energy reflected from various objects within the illuminated beam C. So here the transmitted energy is A, right, focused by antenna into a beam, that is B, and then C is the energy reflected or back scattered from various objects, right. Now subsequently, electronic system store this data in the form of two-dimensional image of the surface, and then it will be transmitted to your ground station and subsequently it will be analyzed, right. In microwave remote sensing, polarization plays a significant role. So here the polarization of the radiation can be used as an advantage, right. So how? Let us see. So let us understand first this polarization. What do you mean by polarization? So polarization refers to the orientation of the electric field, and most radars are designed to transmit microwave radiation either horizontally polarized or vertically polarized, right. So I have a figure for you. Here you can see the active microwave radar sensors. What they will do? They will illuminate the surface, but how they will illuminate? By emitting some light in microwave region, and how they will be aligned, or the how this electric field will be managed. So either they will be using this horizontally polarized light or vertically polarized, right. So in this case, if you see, this is moving like this, in this case it is moving like this. So one is horizontal, another is vertical. So this is in case of transmitter. Here we are only talking about the transmitter, but do we have the flexibility so that we can transmit horizontal but receive vertical? Is it possible in microwave remote sensing? Then answer is yes, right. So here the combination of polarization are also used in microwave remote sensing, and first one is your HH. So HH means the transmitter will be in horizontal polarization and receiver will be in horizontal polarization. In the next one is VV. So, vertical transmit, vertical receive. In HV, it is horizontal transmit, vertical receive. In VH, vertical transmit, horizontal receive. So, here basically we are making use of the technology and we are trying to extract maximum information using this microwave energies, and basically here we are measuring the backscattered, right. Among these four, the first two, which is actually your HH and VV, they are known as like polarization because both are in same polarization domain. So, first one if you see the HH basically horizontal horizontal. So, they are like each other, vertical vertical, but in the next one these two, they are basically different from each other. They are known as cross polarized. Here you can understand this, how these electric fields have been generated, and this is just for the visualization, right. And here you can see this plane is basically orthogonal plane with respect to propagation direction. So, these two are basically the plane orthogonal to your propagation direction, whereas if you see these signals, so the electric field is basically here and here. So, one is your horizontal, another one is vertical, right. So, in polarimetry what we do, we acquire, process and analyze the polarization state of an electromagnetic field. So, this is what we are going to use in microwave remote sensing when we are talking about the polarization or pulsar, polarimetric SAR, right. So, in polarization you have first one is HH, where the transmitted and received energy both are in same polarization, that is horizontal. In the next one you have HV. So, first one is transmitted is in horizontal direction, horizontal polarization, and received is vertical polarization. In VV both are vertical, in VH the transmitted is in vertical, whereas received in horizontal. So, if we divide this into two groups, so HH and VV, they are known as like polarized, and HV and VH are known as cross polarized. I hope this is clear to you. Now, here we have seen all the four cases, but can we get some additional information by changing this polarization, whether in transmitter or in receiver? Yes, we have some different information when we are using HH, when we are using HV, VV or VH. So, what exactly we will get? So, that I am going to show you some example. So, this is one HH image. So, here the transmitter has used horizontal polarization and receiver in horizontal polarization. Here VV, then third one is HV. So, you can see all these three images, and can you find out the difference or some additional information which you are getting in different polarization? So, here if you see this HH, this particular area is actually better than others, right. If you see VV, you can see this particular area, this is water body. So, here you can find some features which was not visible in this one and not even this one. But if you see HV, your settlement or the building information or the geometry of smaller objects are better, right. So, if we use this, our information will be different. If we use this, our information will be different. If we use HH, our information will be different. But can we use our basic understanding about remote sensing and how do we visualize these images? So, I hope you remember this color composite. So, in case if we can generate a color composite using these three images, whether our information will be different or it will remain like only like this or this or this. So, let us see, when we combine HV, HH, VV together to generate a color composite, let us see. I hope you can easily find out the differences between the first, second and third image, and this is the color composite image, right. So, here the information which has been highlighted by this HH and VV and HV all are merged together, and all the information captured by these three different combination of polarization has been included here. So, in case if you find a data in all these 3 or 4 polarization, you can generate a color composite and you can make use of this polarization to extract your target in better way, right. So, remember, here in this course I am going to teach you all the basic understanding as well as the advanced processing of this remote sensing data. Doesn't matter whether it is in optical or microwave domain, but you have to select the best method which is giving you best result for your application or your problem, right. So, here I have listed some of the satellites which are working in microwave domain, and this is not the complete list, this is selected satellite. So, first one is CSAT, next is ERS 1 and 2, JRS 1, RadarSat 1, CERSI, NVSat, RadarSat 2. So, these satellites are available in space and the data sets are also available to us. Some of them are paid, some of them are freely available. So, in case if you want any of these data sets or maybe the recent launched data sets, so you have to contact the space agencies, and if it is freely available you can directly download them. If it is paid, then you have to do the formalities, right. As I mentioned earlier, this microwave remote sensing is completely different from your optical remote sensing. So, here the imaging technique which we used in optical remote sensing, that is not followed here. So, to understand that, you have to understand what are the different imaging techniques we have in microwave domain. So, first one is strip, then ScanSAR, then spotlight, then pulsar, then InSAR, then ISAR, right. These are different imaging techniques available in microwave domain, and now let us see some of them to understand how they are playing big role in your data generation. In this first one, strip mode, you can see this particular flight is carrying a active remote sensing sensor and which is illuminating this particular surface, and it is sensing this area in strip. So, first strip will be generated, then next will be generated, then so on, and subsequently using these strips image will be formulated, right. In the next one, here in ScanSAR, what you will do, you will acquire the images in frames and the frames will be used together to generate the image, right. In the third one, you have spotlights, and spotlight again this will be generated like this. So, one object will be seen from 2 or 3 different position and then you will generate this complex images. So, here if you compare this strip, ScanSAR and spotlight, you will find the difference in the swath. So, here when we are using strip mode, this 30 kilometer swath has been reported. When we are talking about this ScanSAR, this 100 kilometer was reported. Then spotlight, this is 10 kilometer. So, the swath is basically the width of your image, right. So, in that width you will have several pixels. So, here also you will have pixel, but the calculation of spatial resolution and others will be different. So, in microwave remote sensing, it is interesting to know about this side looking radar system operation. Here let us understand this particular flight is carrying a active remote sensing sensor. So, it will start illuminating or transmitting the microwave signal, which will subsequently reach to your target. So, here you can see once it has reached to this particular position, it has already interacted with the first object, right. As soon as this object get this transmitted signal, what will happen? Your back scattering will start. So, the back scattered value will start traveling towards your sensor, and the same time this transmitted energy will keep on traveling to your next target, and once it reaches to this tower, then it will again send back the next echo, right. So, the back scattering will start from this tower as well as from this house, depending upon their position and the time when they interact with your transmitted signal. So, once it is over, then it will reach to your sensor, and then they will be recorded separately and your microwave image will be generated, right. So, here already everything is mentioned. So, these are basically radar pulse from transmitter on board aircraft, this yellow colors, right, and the return signal from tower, they are in green, and return signal from your house, they are in gray color, right. I hope this is clear to you. Now, let us understand this imaging radar system, how we can do this imaging and what are the different types of imaging radar systems available nowadays. So, first one is side looking airborne radar system, or it is also known as real aperture radar, and the next one it is synthetic aperture radar, and in the first one, the real aperture radar, basically this refers to fixed length of antenna. So, let us understand this. Assuming this is my microwave sensor and these are antenna, and your transmitter is located here and this is your receiver. So, this will illuminate this surface, right. So, once we receive this back scattered value, it will be stored and it will be transmitted further. So, here in this case, in real aperture radar, we are referring the fixed length of antenna. So, this is the antenna, right, and aperture means antenna. So, real aperture means antenna radar. So, we are not going to synthesize or we are not going to mathematically change the length of this antenna in RAR, right. In the next category, we have SAR, right. In SAR, basically what happens, the 1 meter antenna can be synthesized electronically into a 600 meter synthetic length. So, here we have used fixed length, here we are using synthetic length, which is synthesized in maybe multiples of the real value, and commonly used in airborne and spaceborne radar system. So, this is more popular because here you do not have to make big antennas, only mathematically or electronically you will synthesize the length of the antenna into more, right. In microwave remote sensing, the distance between transmitter and reflecting object can be estimated using the measured signal echoes. The measured signal echoes means backscattered value. Since the energy propagates with the velocity of light c, right, c is known, the slant range to any object can be calculated. So, what exactly we mean by slant range? So, remember, range term is used for distance, right. So, the slant range is equal to Ct by 2 and t is basically your time. So here we are measuring this time from this transmitter to your surface and how much time it is taking to reach to your sensor, the backscattered value. So here that's why we are using this 2 factor. Since the time incorporated in equation, time measured for the pulse to travel both the distance to and fro the target, the factor 2 is used in the equation, right. This is very simple. I hope you have understood. Now the next point is sensor slant range. For that I would like to use this animation. So here this is basically your surface and you have a sensor located here, right, and you can easily draw the horizontal plane along which your flight is moving, assuming there is no change in the altitude, sudden change in the altitude. Here you can draw a tangent and this is basically horizontal plane you have drawn, right. And once you just see vertically down from your sensor or from your satellite or from your airborne platform, what will happen? You can easily mark this nadir. So nadir is vertically down projected point on the ground, right. And as we know that this will illuminate this surface with this FOV, right. And once you have this image generated for this particular area, you can easily find out the center of the image, right. And once you have this center, the distance between this center of the image and the flight or the space bound sensor, that is referred as slant range. And image center already you know, this is your nadir, right. This is your horizontal plane and this is the direction of your zenith. So zenith will be like this, right. In microwave remote sensing, we use different nomenclature for the geometry. So let us see what are the different viewing geometry we use in this microwave remote sensing. So the first one is, let us understand, similar to optical system, the platform travels forward in the flight direction A. So the flight direction is A with the nadir B directly beneath the platform. So if we draw, it will be like this. So this is the direction of your flight, this is your nadir, which means vertically down projected point on the surface, right. So this angle will be 90 degree. Now with some angle we actually illuminate our surface. So the microwave beam is transmitted obliquely at right angle to the direction of the flight, illuminating a swath C. So swath is your width of your image. So here it is C, which is offset from nadir. So this is your nadir and this is the offset. So if we calculate, this will be your slant range, sorry, this has to be straight line. So suppose this is the center of the image, so this angle will be your offset. The range D refers to the across track dimension, right, this one, while azimuth refers to the along track dimensional parallel to the flight direction. So this is E. So D and E. So I think nomenclature is clear to you. The direction is A, nadir is B, swath is C, range is D, right, and azimuth is E, and this is basically 90 degree, right. In this diagram, the nomenclature for the geometry of radar data collection has been highlighted. So let us understand. Again, this is carrying your sensor and this is definitely our earth surface. Now let us draw the perpendicular on this surface, right. So this will be this line, and if we are illuminating this area, this angle will become incident angle, and the angle between your illuminated beam, right, and the perpendicular, this is basically your nadir. This angle is known as look angle, right, and the horizontal plane which we have drawn, which is basically which tells you about the direction of your flight along which your flight is moving. So, the angle between this and the beam will be depression angle. I have another image to explain all these geometries. So, let us see here. This is your satellite or the sensor, does not matter where it is, it can be in space or maybe airborne platform. Now, let us go one by one. Here you can see this is the image which has been generated, right, or we are trying to generate. Let us understand in this way. Now, in this image, this is basically your sensor, and you can draw the nadir by looking downward, and which will make 90° with the surface. Here you have this image which we are trying to generate. So, now let us see what are the different nomenclature we have for this geometry. So, just see, I am going to highlight all these terms one by one. So, this is your depression angle, right. So, here the angle between the slant range and horizontal plane is known as depression angle, right. Is it clear? Now, next one is look angle. This is with respect to your nadir. So, here you are going to measure this angle and this will become your look angle. Now, next is your incident angle. This is with respect to perpendicular on the ground, and this angle will be your incident angle, right. Can you see this one? Now, next one is azimuth in this direction, and next is near range. So, near range is this one, right. So, in near range and far range, what is the difference? Basically, near range is the range which is close to your nadir, far range which is far from your nadir, right. And this is slant range. I hope you remember the distance between the center of the image and the satellite or the sensor, that is known as slant range, right. And this is basically your beam width, and this is the ground range. So, just to make sure whether you have understood this or not, I am going to repeat this once again, because this is very important to understand this geometry, right. In this image, this has been used to represent a sensor, active microwave sensor, and here you have depression angle, which is the angle between this horizontal plane and this slant range, then look angle, then your incident angle, azimuth, near range which is close to your nadir, this is far range which is far from your nadir, there is this slant range, and this is the beam width. This is how we are going to generate this image, and this is the ground range, right. I hope all these things are explained in very simple manner. Now, let us see how we can explain this. Like, sometimes you have to write some definition, or sometimes you have to write what do you mean by near range, far range, then how will you write. So, by using that diagram, as well as you can use this text, how to explain all this viewing geometry. So, near range, the portion of image swath closest to the nadir track. Far range, the portion of the image swath farthest from the nadir track. The next one is depression angle, the angle between horizontal and a radar ray path. Slant range distance, the radial line of sight distance between the radar and each target on the surface. The next one is ground range distance, the true horizontal distance along the ground corresponding to each point measured in slant range. Then incident angle, the angle between the radar beam and the ground surfaces. And the last one is look angle, which is the angle between vertical and a ray path, right. So, the same thing has been again put on this image, and you can see here we have highlighted this slant range, look angle, range, near range, and this is the far range. In between, because if this is 100 kilometer long strip, then you can have mid swath, near swath, far swath, because depending upon the view angle or the angle from this nadir, look angle, your image will be different, right. Here this is the swath and this is the area which you are trying to acquire, right. How do we define range resolution? So, range resolution is basically an ability of a radar to distinguish between two radars in the range direction. And here in this diagram, this particular sensor which is located here is releasing the pulses, right, and where we are trying to illuminate this A and B target, or let us consider this whole area, right. So, in this case what will happen? We will release the pulses which will reach to our surface at some point of time, and then once it interact with the target, then it will start giving the back scattering echoes, right. So, the back scattered values will be sent back to your sensor. Here the length of the pulses plays very critical role in order to identify these objects in microwave remote sensing data. So, if A minus B, that means the distance between A and B is less than PL by 2, then we cannot identify these objects in microwave data. But if A minus B is bigger than PL by 2, right, then you can divide or you can identify these objects, right. So, for two different objects, it is necessary that the antenna should receive the separate back scattering signal from both objects. Otherwise, what will happen? They will get merged with each other. So, I hope you remember this optical remote sensing where you have concept of pixel, spatial resolution. So, if one pixel is having a tree and a house together, what will happen? Basically, we store only one DN number here. So, we cannot resolve this DN number in terms of house or tree, right. So, but if we have several pixels here, then we can easily find out different parts of this tree and different parts of this house, right. So, in that case it will be very easy. The same thing applies here, where the two different objects, it is necessary that antenna should receive separate back scattering value, then they will be identified as two different objects in your image, right. If there is any overlap between this and this, then what will happen? Your image will be get blurred. Here in this case, what is happening? The range resolution and ground resolution. How do we define these two terms? So, the pulse length PL is basically C tau. I hope it is understood in the previous slide. So, basically this is your tau, right, and this is also known as pulse of the length, where C is your speed of light and the values are known. The complete object is imaged or distinguishable if the slant separation between the object is greater than Ct by 2, right. Therefore, RSR is C tau by 2 and ground resolution is C tau by 2 cos beta, right. I guess it is clear from this diagram. So here basically we want to make sure that A minus B is less than PL by 2 or C tau by 2, then these will not be resolved in your image. But if you want to resolve, then what will happen? The slant separation between the object should be greater than C tau by 2, right. Here in this case, what is happening? We have already understood this part, depression angle and look angle, and now we are having a object here, or this object or this place we want to sense, right. So what we will do? So we will illuminate from here, and that illuminated or the transmitted signal will reach to this particular surface, and then it will interact with this area or the object. So the slant range resolution does not change with distance from the aircraft, right, the slant range resolution, because this is one angle at which we are looking this particular area. So it will not get affected by the altitude, right, distance from the aircraft, but ground range resolution will get affected when you are changing the distance between object and the aircraft. Ground range resolution becomes smaller if increase in slant range resolution, right, and when the depression angle effect is considered, the ground resolution in the range direction can be estimated using this formula. So here C tau by 2 cos theta d, and theta d is basically here, and tau is the pulse duration, right. I have a problem for you. A SLAR system transmit pulses over a duration of 0.1 microsecond, then you have to compute the range resolution of the system at a depression angle of 45 degree. So first you have to understand this question, then you draw the geometry, and then it will be very easy. So before solving, you don't see my next part of this lecture. First you solve yourself, then you go for the next video. Now here we have drawn, this is the depression angle, this is look angle, and this is slant range resolution, this is theta d. So what value we have? We have depression angle of 45 degree and this pulse over a duration of 0.1 microsecond. So you can use this formula and you can calculate the value. So here this result will be 21 meter, right. We have already discussed this synthetic aperture radar in the previous slide. So where we had this RAR and synthetic aperture radar, right. So let us see what exactly we can do in synthetic aperture radar. So radar antenna can be synthesized electronically into longer synthetic length. So this is the advantage when we are going for SAR. So SAR is synthetic aperture radar. Synthetic aperture radar, which can be airborne or spaceborne, could collect data over a large distance as it is collected from physically long antenna. So this is the advantage you have when you have SAR. Now in this slide, basically I want to explain you how this synthetic aperture radar works. So here in the first position and the third position, you can compare, the position has been shifted, right. So what is happening here? This is the beginning of the target view. So from here it will see this particular target, then this is the length of synthetic aperture radar. And how it is done? Because the signal will be transmitted from here and received from here or here, right. That is the length of the antenna we are going to synthesize, and this is the flight direction, this is end of target view. So if you see, this particular target have been targeted from the beginning, right, and here it was done. So, this antenna may be 1 meter, right, but this distance could be 1 kilometer. So, this has been synthesized using this electronic device. So, here this is the flight direction, this is the end of view, this is basically the first view, then second and third view, and this is the point target, right. I hope you have understood this one. Now, let us understand how we can image this particular object using this synthetic aperture radar. So, assuming the position of this target here, and this is synthetic aperture radar, and if you draw a perpendicular vertically down and which meets to your ground, that will be your nadir, which is here, right, and then you have ground track, and you can obviously see, as we have seen in the previous slide, you can target this particular object either from here, or you can illuminate from here and you can sense from here, right. In full aperture, basically this is known as single loop. When you are having two loop, that means you are dividing into two parts. In 4, it will be known as 4 loop. So, in case if you are having single look image, that means it will have certain limitation. When you are having 2 loop, that means you are going to add more information. When you are having 4 loop, it will have further more information. So, you can increase this loop depending upon the device you are going to use, or the technology or the technique which you are going to follow, right. Here in this case, the single look image will look like this, then 2 look image will look like this, 4 look like this, 5 look like this, 10 look like this. So, obviously, the 10 look will have maximum information about the area or the target, right. So, in microwave remote sensing, especially in synthetic aperture radar, since we are going to synthesize the length of the antenna, we can image the area from maybe 2 or 3 or maybe 4 positions, and then accordingly we can generate multi-look images, right. So, how basically this image has been generated? Using the radar equation. So, you can see here we are using this power transmitted towards the target, then GT is basically gain of the antenna in the direction of the target, R is range distance, and sigma is radar cross section or effective scattering area of the target, then AR is basically effective area of the receiving antenna. Using this, we have calculated the received power, right. Here further we want to modify it because we want to make it simpler, and then finally this is your equation for power received, right. In back scattering, the coefficient plays a very significant role. So, back scattering coefficient is defined as the amount of back scatter per unit area, right. So, this is sigma naught and this is basically sigma divided by A. So, sigma is back scattered value and A is your area. So, that will become per unit area, and it depends on two main things. The first one is the target and the second one is the system parameter. So, the target will play a very critical role here because roughness, geometry, moisture content, they are the properties of your target, whereas the system parameter like which wavelength you are using, what look angle you are using, what polarization you are using, that will also affect this back scattering coefficient. So, in case if you are having different back scattering coefficient for the same target, that means either you have changed this target properties or the system parameters have been changed. Now, the signal to noise ratio, This is very important to assess the strength or the quality of your signal. So, here the signal to noise ratio is calculated using this PR divided by PN. So, PR is basically your KBT, right, and K is basically Boltzmann constant, B is your bandwidth, and T is receiver's noise temperature, and Pn is basically our signal that we have already discussed in the previous slide. So, this is the equation from radar equation, and Pn you can calculate from here. So, once you are having this, you can easily calculate what is the strength of your signal or what is the quality of your signal using this signal to noise ratio formula, right. So, here you can see if Pn basically your noise, thermal noise. So, if Pn is more, what will happen? The value will be less, right. If Pn is very less, then PR will be more, right. So, if the signal to noise ratio is less or low, accordingly you have to decide what is the quality of your information. So, now as we discussed in the previous few slides, different types of imaging technique. So, this is another type of imaging technique which is known as interferometric SAR, which is also known as INSAR. So, INSAR is very popular. So, synthetic aperture radar imaging system with interferometric configuration is known as interferometric SAR or INSAR, right. So, what it does is it allows accurate measurement of the radiation travel path because it is coherent. Measurement of travel path variation with respect to satellite position and time of acquisition allowed to generate digital elevation model, right. It can provide centimeter level information related to surface deformation, right. And the next point is high resolution digital elevation models or surface change map due to earthquake, land subsidence, glacial movement, volcanic activity, land use, land cover change can be estimated accurately using this INSAR. Why? Because it is something like photogrammetry. I have taught you, if you are changing the position of the observer and if you see the same material from two different positions, the information will be different and you can exactly pinpoint their properties, especially the geometric properties. So, that is why in INSAR you have capability to measurement of travel path variation with respect to satellite position and time of acquisition, and which actually allows us to generate the digital elevation model, and it can be centimeter level accurate. High resolution digital elevation model or surface change maps are very common product of from this INSAR, and the application of this INSAR is in land subsidence, earthquake, glacial movement, volcanic activity, land use, land cover change. So, these are very popular application of this INSAR technology, right. So, how do we do this SAR interferometry? So, basically we need at least two radar, right. We can have this two different radars or radar imaging from two places, right. So, maybe this itself will move after certain time and then it will see that object from there, but the time lag should not be high. The phase is measure of how far the wave has traveled, right. So, if it is here, then it will be 0, then 2 pi, 4 pi, 6 pi, accordingly this phase difference will be measured. In general, the relationship between phase and distance is 2 pi d by lambda. So, that is, if we have travel by a wavelength d is equal to 1, then the phase length has changed by 2 pi. That is why this is 2 pi, 4 pi, 6 pi, right. So, this is in case of INSAR. In INSAR, the phase information is very important, and we are generating this phase information. Why? Because we want to effectively calculate or estimate the random noise in a single SAR image, because the phase are randomized by all the scattering of the earth surface, right. So, your phase image will look like this, and once you have this phase image, then you can predict your material. However, if we view from another position very close to the first, then the difference in phase tell us about the differences in the distance. So, basically, if we have measured the same target from two different locations, we can generate the phase information, and once we have the phase information, you can easily identify the differences in distance, and then you can use this data. So, here if you see normal baseline, that is the distance between these two satellites, right, and this is the phase difference. So, here the phase difference is this distance, and the returning radar signal is 1 and 2, and image point at the same location along this arc. SAR phase difference is used to point out the exact location, because in DM generation you need to be very sure about the location, and basically the accuracy has to be more. This is our earth surface. So, difference between two path length related to the difference in phase of the received electric fields, right. So, in interferometry, basically we generate coherent image and phase information. So, the entire image of the phase information is known as interferogram, and an image of the coherence, that is the correlation between the two images. So, if the coherence near 1, that means the phase information is reliable, right, and the image have high degree of correlation, because you have generated both the images from different position. Now, the coherence less than or equal to or close to 0.3 means the image have low correlation and basically it is noisy. In this case, the phase information is probably not useful. So, before analyzing your phase information, right, or the interferogram, you have to generate the coherence image, and the coherence image value need to be checked for the consistency or the accuracy of your data, right. In microwave remote sensing, the level of information is different, the quality of the information is different. So, let us understand what exactly we can do here which we cannot do in optical remote sensing. So, radar signal can penetrate vegetation cover and soil surfaces. Why? Because wavelength is long. Now, the next is depth of penetration is significantly get affected here, because the depth we are saying it can penetrate, but how far? So, that defined by moisture content of your surface and the roughness and the incident angle. So, it is very important if you are going for subsurface studies or the geometry related studies or the moisture content estimation, then you need to understand these are the limitation of the microwave remote sensing data. So, it can give you the information, but you need to take care of all this. Maximum information about this penetration can be achieved with the longer wavelength, and several application of INSAR have been reported. You can see many papers in civil engineering, in mineral exploration, cartography or mapping, remote sensing and geodesy, and military application. So, if you see civil engineering, alignment study, site selection, urban development, erosion, watershed, drainage, water runoff, flood control, etc. are common application, right. In military, display of landform, then airport avionics, missile guidance, then cross country visibility. So this is actually a brief list of the application of INSAR data, right. You can go through it, you can search some papers where people have already used this INSAR technique. So altogether microwave remote sensing has application in all the areas. So starting from geology, meteorology, then topographic cartography, security, sea ice oceanography, forest, land use, land cover, agriculture, hydrology. So everywhere it can be used, provided you should take care of the data generation and the analysis. And here we have some list like soil moisture mapping, vegetation mapping, soil temperature, snow cover and snow water equivalent, sea ice mapping, atmospheric temperature profile, humidity profile, precipitation, ocean application, right. In other application like agriculture and forestry, soil moisture, already this soil temperature I have mentioned, right. Geology, hydrology, oceanography, snow and ice, land use, land cover, urban analysis. So you can use this technology, provided you should be able to interpret the data. So before that you need to go through all these basic, understand the technology, and then accordingly select appropriate data for your application, right. So that's all for today. Thank you.